Hi everybody, and welcome to the top of page 43 in the workbook. In this video, we'll be talking through some of the theorems that we gave a kind of a graphical introduction to on the previous page. Okay, so starting with the dimension theorem, that was the first one that we kind of conjectured. Okay, again, what that says is that if you have a linear transformation from V to W, then the dimension of the domain V breaks down as the dimension of the null space plus the dimension of the range. Okay, and then theorem 2.4, that was another one that came up that said that linear transformation is one-to-one if and only if the null space of T just contains the zero vector. Okay, and then finally theorem 2.5, in our diagram, we just kind of convinced ourselves that the equivalence of A and B might be plausible. Okay, that if we know that the dimension of V and the dimension of W are the same, then T being one-to-one and T being onto are actually equivalent conditions. Okay, now we could prove all of these things, but that would take quite a while. So what I'd like to do is just to pick one of these and prove that. Okay, see if we can prove theorem 2.4. All right, so in the space down below, we'll do that here. Okay, and notice that this is an if and only if statement, so we're going to need to do two directions here. So in the forward direction, we would be assuming that T is one-to-one. All right, what do we want to show? Well, we're going to try to show that the null space of T is 0. Okay, or the null space of T is the set that just contains the zero vector. Okay, well, basically what we're trying to do in this direction of the proof is a set equality. The null space of T is equal to the zero vector, so we'll start by just making the observation that we already know that since T is a linear transformation, T of the zero vector is equal to the zero vector. And what that means then is that the zero vector is in the null space. Okay, do you see why that's true? Okay, because we just demonstrated that if you substitute the zero vector in, you get the zero vector out. Okay, so that input zero vector has to be in the null space. Okay, but what we've just shown then is that the zero vector is actually a subset of the null space. Okay, because we just showed that the zero vector is in the null space. All right, now we need to go the other way and convince ourselves that the null space is a subset of the zero vector. Okay, so we'll use the pick-a-point method. Choose any vector v that's in the null space. Okay, well, by definition, that just means that if we substitute v into our linear transformation, we're going to get the zero vector out. But notice, we already made the observation that that zero vector is also what we would get if we plug the zero vector in. And now we're going to use our assumption. T is a one-to-one function, so what has to be true if we plug in both v and 0 and get the zero vector out? That forces v to equal the zero vector. That's the only way that this can be a one-to-one function. Okay, so let's say it this way, because T is one-to-one, we have v equal to the zero vector, and that tells us that the null space of T is a subset of the set containing the zero vector. Okay, so if you look back through that argument, we have shown containment in both directions. Okay, and that proves that the null space of T is equal to just the set containing the zero vector. All right, what about the reverse direction? Okay, well, there we'd be going the other way and starting with the assumption that the null space is the set containing just the zero vector. Okay, and we want to show now that T is one-to-one. Okay, remember what the definition of one-to-one is. It's just, or one way to formulate it is to say that if two outputs are the same, t of x and t of y, that means that the inputs that produce those are the same. Okay, that's what we're going to try to show here. Okay, so let's see if we can do that. So if we start with the assumption that t of x equals t of y, then we can subtract the t of y to the left-hand side, and we get t of x minus t of y as the zero vector. Okay, and then notice that we can rewrite that as t of x minus y equals the zero vector. Do you see why we can get away with doing that? Okay, we know that t is linear. Okay, so we're just using that property of linearity here. Okay, but if t of x minus y is equal to the zero vector, that means by definition that x minus y is in the null space, okay, because when we substitute it in, it maps to the zero vector. So if we want to give a reason for this set, we could, or for this step, we could say that this is the definition of the null space. Okay, now we kind of come to the critical step here. If x minus y is in the null space, we assume that the null space just contains one vector, the zero vector. So that means that x minus y has to equal 0. That's the zero vector. That's the only possibility. And if that's true, we can add y to both sides and we get x equals y. That's exactly what we wanted to show. And therefore, t is indeed 1 to 1. All right, and that's our proof.